Welcome to this video where we continue to talk about content in the book Introduction to Nonlinear Control. And in this video I'm going to talk about content contained in chapter 17, focusing on a derivation of the extended Kalman filter into continuous time setting. And then briefly at the end I will also talk about a couple of extensions which can then be found in detail in the book. In the video on chapter 16, we have focused on linear systems. X dot is equal to ax plus bu, y is equal to cx, and for this setup we have derived an observer such that the estimated state x head converges to the true state of the system x. Here we extend this concept in the derivation of an observer for nonlinear systems with a general right-hand side f of x, u, and with an output equation y of t is equal to h of x of t. But we are going to use a similar structure in terms of the observer dynamics. Namely, we are going to introduce again an estimate of the state x head, and then this estimate of the state follows the dynamics. So our model here plus an output injection term L of t, now time varying. So we are going to design this L of t time varying, taking the mismatch between the actual output of the system and the estimated output into account here. So important to remember now again, x head denotes the estimate of the state and LT is a time-dependent output injection term which we want to design on the following slides such that x head converges to x. And as in the case of the linear system setting, we are going to do this derivations in terms of the error dynamics, meaning we are going to define E as the mismatch between the actual state x and x head, which allows us then to write down E dot in this form here on the right hand side. But we now realize that we are unable to get rid of the variables x and x head here, meaning in the linear system setting we were able to rewrite this right hand side in the form again that we only had E on the right hand side and u, but it was not dependent on x and x head. So here we have to work a bit harder, and as a first step what we're going to do is we're going to linearize the function f around the solution x head u, so that we get a time varying linearization by taking the derivative with respect of f with respect to x and then evaluate this linearization along the estimated state trajectory. And similarly we define c of t by taking the derivative of the output map. If we then additionally rewrite the term f of x, u in terms of E and x head, then it follows trivially that if we take the mismatch here and evaluate that at 0, then that this term is equal to 0. And what we can also see if we then take the derivative of this component here with respect now to E and evaluate it in E is equal to 0, then we end up with this matrix A of t. And similarly, if we do the same calculations with respect to the output map, then we end up with C of t. As a next step now, to essentially get rid of the components x and x head here, and to be able to rewrite that term, or approximately rewrite that term in terms of the error variable E, we can use the Taylor approximation at E equal to 0, but with respect to x head. This allows us then to actually write E dot is equal to a similar term as we had before, A minus L C times the error variable plus plus an error term, depending on E, X, and U. So let's remember what we want to design. We want to design L such that the origin of this system here is stable or asymptotically stable. To do that, we are going to consider a candidate Lyapunov function. Candidate Lyapunov function because we haven't shown the decrease property yet, and we have not defined this matrix P of t yet. We simply assume for now that P is positive definite for all times t. And yeah, that will be the next step, designing P and L in such a way that the origin of this system is asymptotically or exponentially stable. Before we proceed with to some extent tedious calculations, I want to point out a particular helpful lemma that we're going to use on the next slide that allows us to calculate the derivative of the time derivative of the inverse of this positive definite function here, simply by calculating the inverse of the function and the derivative of the function. So instead of using this expression here on the left-hand side, we can calculate and use the expression on the right-hand side. And that's actually kind of a short exercise that might be interesting to prove that this equality here holds. Okay, but having said that, now we want to show that this candidate Lyapunov function is indeed a Lyapunov function if we design L and P appropriately to then guarantee exponential stability of the origin of our aerodynamics. So if we calculate the derivative of this function v of e of t with respect to time, then tedious calculations first give us this expression where we then can plug in our aerodynamics and where we can replace the expression of p dot to the power minus 1 using the formula from the previous slide. And then finally we end up with this expression here, meaning a quadratic term with E transpose and a time-dependent matrix in the middle, and then a term depending on our error term here. As the next step, we define our output injection term L of t in this way here, meaning in terms of the at this stage unknown function P of t depending on C and Q, which is structurally the same as the derivations or as the formulas in the linear setting, with the only difference that there P was constant, C was constant, and Q was constant. If we use this expression here, this expression here in the expression up here, meaning we replace L, then the derivative of V can equivalently be written in the form here. And then we need to specify how to define P dot, and we are going to specify it in the way that it satisfies this so-called differential Riccati equation. So we have seen already algebraic Riccati equation. Now here we're making use of the differential Riccati equation. So quadratic matrix equation where we essentially use some of these components here in the derivative of V dot, but also add a positive definite matrix R here. Meaning in this stage kind of Q and R are our design parameters which we can select as positive definite matrices. If we then replace P dot of T in V dot, then we end up with the expression here, where we have a positive definite matrix here in the middle in terms of R minus 1, which means this matrix here, or function, because this is actually time dependent, even though this is not explicitly written here, this is a positive definite function. P is a positive definite function, meaning we have a positive definite term here. And we still have our error term here. But for E sufficiently small, due to this negative sign here, we indeed have a decrease of the candidate Lyapunov function, which then implies that we have a Lyapunov function here, which allows us to conclude local exponential stability of our aerodynamics. So if we want to summarize these steps, or the important equations of the extended Kalman filter here, then we have started with this nonlinear system. We have introduced observer dynamics of this form here, where we still had to design the output injection term L. Using these three equations here, we could formulate the aerodynamics. And then if we have designed L of t in a particular way as shown on the previous slides, then we get local exponential stability of the aerodynamics, meaning x hat converges to x of t locally. And to implement the extended Kalman filter now, or this observer here, we need to implement this differential equation with respect to x hat, containing additionally the terms, or containing here the term L of t, which we have defined on the previous slide. And additionally, we need to solve the differential Riccati equation, which is an n by n matrix equation, depending here on the linearization. So that was our matrix A of t, again A of t, and then C of t, and C of t, and Q and R are design parameters, meaning positive definite matrices, which we can design. So this allows us then to simulate these equations, and using the output information here, and which allows us then to get an estimate of the state x. So here, this was one possible derivation of the extended Kalman filter here in continuous time setting, in the deterministic setting used here based on the linearization around the current state estimate x hat. So we used Taylor approximation and then first order Taylor approximation. One can also use higher order terms in the approximation and then motivate that accordingly to get alternative variations of the extended Kalman filter in terms of the unscented Kalman filter. We've used here derivations in the continuous time setting, but one can also do these calculations in the discrete time setting, leading to similar results, but slightly definitions of the output injection term, of course. These calculations here on the extended Kalman filter don't take constraints into account. When we moved from optimal control to model predictive control, we had a way to take constraints into account. Similarly, we can use similar methods here, where we can move to moving horizon estimation, meaning from linear quadratic controller LQR controller designs. We moved to the Kalman filter. Here we can go for nonlinear setup from model predictive control to moving horizon estimation. Okay, but this concludes the talk here, the short presentation on a possible quick derivation of the extended Kalman filter in the continuous time setting using deterministic setting. And then in the next video, we are going to talk a bit about content contained in chapter 18, discussing other nonlinear observers for nonlinear systems. And that will then also conclude the presentations for this book.